The two propositions above discussed the algebraic properties for the ring of p-adic integers, Zp. In this section of the video series, we are going to discuss some topological properties for Zp. And in particular, we're going to introduce a metric on Zp. To that end, we're going to introduce a very important definition and notation as an immediate corollary to proposition 2. Let X be a non-zero element of Zp. In view of proposition 2, we're going to write X in the form Pnu, where n is a non-negative integer, and u, as in this proposition, is an invertible element, leaving in this u the subgroup of invertible elements of Zp. From proposition 2, we know that this expression is unique. Now, the integer n here will be called the p-adic valuation for X. And denoted by Vpx. If X is equal to 0, then we make a convention that Vp of 0 is equal to positive infinity. And now let us check the following simple properties for Vp of X. First, if you take the product of two elements in Zp, what is the p-adic valuation for that product? It turns out that this is equal to the p-adic valuation of X plus the p-adic valuation for Y. This is easy to guess because the p-adic valuation takes the exponent n from this factorization for X. So you may imagine that it might behave like a logarithm function. This is easy to check. First, if X or Y is equal to 0, then the left-hand side is just Vp of 0, and the right-hand side is Vp of 0 plus something. Then we have infinity equals infinity. So this equality is trivially true. And now suppose both of them are non-zero. Then we may factorize them as follows. X equal to Pmu and Y equal to Pnv, where m and n are non-negative integers and u and v are invertible elements in Zp. Immediately, we have their product equal to Pm plus n uv. Now, because u and v are invertible, and so is their product, so u times v is again in u. But the unique factorization from proposition 2, we know that the p-adic valuation of X times Y is m plus n. And m is the p-adic valuation for X, and n is the p-adic valuation for Y from our assumption. And this verifies the first property. The first property is about the valuation of the product of two elements. And you may wonder what happens to the p-adic valuation of the sum of two elements in Zp. There's no perfect equality for this in general, but we have an inequality. The p-adic valuation for the sum of two elements is always bigger or equal to the minimum of p-adic valuations. And now let's check this. Again, we need to single out the cases when x is equal to 0, or y is equal to 0, or x plus y is equal to 0, where the corresponding p-adic valuations could be equal to 0. If x is equal to 0, then Vp of x plus y is just equal to Vp of y. And the right-hand side, because the p-adic valuation of 0 is equal to infinity by our convention, so this guy will simply reduce to Vpy. So they are equal. And same for the case when y is equal to 0. Now if x plus y is equal to 0, then this becomes trivial, because the left-hand side is always equal to positive infinity. So this is trivially true. Now we can assume x not equal to 0, y not equal to 0, and x plus y not equal to 0. In this case, we consider the factorization x equals pmu and y equals pnv, and without loss of generality, we may assume that m is bigger or equal to n. And in view of this factorization, we may write x plus y is equal to pmu plus pnv, and because m is bigger or equal to n, this is equal to pn times p to the power m minus n times u plus v. Now, let us focus on this part. And we consider two cases, depending on whether this part is divisible by p or not. In the first case, if p does not divide this part, then we know this is already a factorization for x plus y, because when p does not divide this part, by proposition 2, we know this guy must be invertible. Let me mark the page for this. This is on the page 12 of Sarah's book. By proposition 2, this guy is invertible. Using notations, this guy lives in U. Therefore, by definition of p-adic valuation, Vp of x plus y is simply equal to n, which is clearly equal to the minimum, which is clearly equal to the minimum of Vp of x and Vp of y. Which is clearly equal to the minimum of Vp of x and Vp of y. which is clearly equal to the minimum of Vp of x and Vp of y. Because Vp of x is equal to m and Vp of y is equal to n, and we have assumed that m is bigger or equal to n. And now consider the second case. The second case is when p divides. The second case is when p divide. And now we consider the second case. When p divides Pm minus n times u plus v. In this case, this is not a p-adic factorization for x plus y. And it follows that Vp of x plus y must be strictly bigger than n. Why is this so? To convince ourselves of this, we need to go to the proof of our proposition 2. Recall, in the proof of proposition 2, we take n to be the largest integer such that the nth component of x is equal to 0. And we have shown that after picking this particular n, x will be equal to p to the n times u, where u is the invertible. And this factorization is unique. Therefore, if p divides this second part, it means that this n is not the largest choice, because we can continue factoring out p from here. So this n is not the largest exponent. And by the uniqueness of the factorization, the largest integer, which is the p-adic valuation of x plus y, has to be strictly bigger than n. It cannot be equal to n, because this n does not give us a p-adic factorization, and because this n does not give us the p-adic valuation. Because this n does not give us the p-adic factorization. Because this n does not give us the p-adic factorization. So by uniqueness, that n cannot be equal to the largest possible choice. So this part follows from the proof of proposition 2. Part B. That Vp of x plus y is the largest exponent of p to the L, such that the L's component of x plus y is equal to 0 in L. And the uniqueness of the factorization. And therefore, in this case, the p-adic valuation of x plus y is strictly bigger than the minimum of Vp of x and Vp of y. And this verifies the second property. And it follows from these two properties that the ring of p-adic integers is actually an integral domain. Why? Because if x times y is equal to 0, then by the definition of p-adic valuation, this happens if and only if Vp of xy is equal to positive infinity. But by the first property, the Vp of xy is equal to infinity if and only if at least one of Vp of x and Vp of y is equal to infinity. And this happens if and only if x is equal to 0 or y is equal to 0. So with the notion of valuations, we can easily verify this with just a few lines. You might wonder, why do we care about the ring of p-adic integers Zp is an integral domain? This is because, recall from abstract algebra, we know that integral domains have their corresponding fields of fractions. Namely, there will be well-defined quotients of two elements in Zp, given the denominator is non-zero. And that field will be called the field of p-adic numbers, or a p-adic field. And we will discuss this in the next section. But before that, as I promised, we will first introduce a metric on the ring Zp and show that metric topology on Zp coincides with the subspace topology of Zp inherited from the infinite product of ANs. This is what we are going to do next.